Okay, so now we'll talk about the method of undetermined coefficients. And it's basically a way of deriving the coefficients in a Newton-Cotes formula. Or more generally, it's like any sort of reasonable quadrature formula, which is based on some appropriate linear combination of the function values. If you happen to know that, it's like this quadrature rule is exact for a certain class of functions. Okay, so so let's suppose the following. So let's suppose that the integral from a to b of f of x dx, right, is approximately some linear combination of, say, a0 f of a plus a1 f of b plus a1 f of a plus b over 2 and a2 f of b. Okay, and further suppose that the formula is exact for all polynomials of degree less than or equal to 2. Okay? All right, so the first thing to realize, of course, is that if your polynomials are up to degree 2, right, there is a basis for that function space. So a basis for p2 of x, right, so is a 1 basis, so is 1x and x squared, right? So it's easy to convince yourself that any polynomial degree less than or equal to 2, right, can be obtained. It's like by a unique combination. It's like obtained by a unique linear combination of these functions, 1x and x squared. Okay. All right. So, and because of linearity of the integral, it turns out that all you really need to do, right, in order to guarantee that a formula is exact for all polynomials of degree less than or equal to 2, is that it is exact for a basis for that function space. Okay. So I just need to check this for 1x and x squared. Okay. So one immediate thing should come to mind. It's like when you see this, which is that you have 3 coefficients, a0, a1, and a2, and you have 3 sort of basis functions, 1, x, and x2. And so it's natural to ask whether if you impose the condition that this quadrature rule is exact for 1, x, and x2, you have enough equations to uniquely determine a0, a1, and a2. And it turns out that you do. So let's go ahead and do that, right? So you have the integral from a to b of 1 dx, right? So you know that this is equal to b minus a, okay, on the one hand, and then I'm going to apply the quadrature, the quadrature formula. It's like given on the right hand side. So f of x is going to be identically 1, so this is going to be equal to a0 plus a1 plus a2. So that's one set of equations right there. Okay, then the second equation is that integral from a to b of x dx, right, which we know is b squared minus a squared over 2, right? So that's equal to a0 times fa and a1 plus a1 times f of a plus b over 2, and a2 times f of b. All right, and then f of x now is x, so this gives you a0 of a plus a1 of a plus b over 2 plus a3 of b, and that's equal to, it's b minus b squared minus a squared over 2, and then the integral from a to b of x squared dx, right, is equal to b cubed minus a cubed over 3. Okay, this is equal to a0 a squared plus a1 a plus b over 2 squared, sorry, that's a2, right? Plus a2 b squared. Okay, all right, so you get this system of three equations, and you have three unknowns, a0, a1, and a2, which you're then going to try to solve for. Okay, so you have three linear equations with three unknowns, right, which are a0, a1, and a2, which you want to solve for. And when you solve for this, you get the following, that a1 is equal to a3 is equal to b minus a over 6, and that a2 is equal to 4 times, sorry, a0, sorry about the numbering, a0, and a2 is equal to b minus a over 2, and a1 is equal to 4 times b minus a over 6. Okay, so this gives what is called the Simpson's rule. Okay, which is that the integral from a to b of f of x dx is approximately equal to b minus a over 6 times f at a plus 4 times f at the midpoint, a plus b over 2 plus f at b. Okay, and then which is exact, so the claim is that this is exact for sort of f of x, it's like which are in the space of polynomials up to degree 3. Okay, all right. Okay. So hopefully you get this idea. It's like that, you know, how to do this. And I should say that, you know, the coefficients you get here would have exactly been equal to the coefficients you had gotten with the Newton-Cotes formula for n is equal to 2, right, where you had sort of constructed an interpolating polynomial, right, out of Lagrange polynomials, and you can compute the coefficients by integrating the Lagrange polynomials from a to b, basically. Right, okay, so let me say something about the error of the Simpson's rule, right? So the error, sort of the error term associated with Simpson's rule is the following, right? So this is negative 1 over 90 of b minus a over 2 to the 5th power times the 4th derivative of f at some unknown point c, where c is in the interval from a to b. Okay. All right. So that's just the error term it's like you have. And of course, it's like in order to compute the error, it's like explicitly you need some sort of bound on the derivative, right? So the remark is that in order to use the error term, right, you need to estimate a bound. You need an estimate on the derivative. Right? Well, or a bound, if you will. Okay, and so sometimes you can do that, and that's oftentimes then allows you to, so if you have a bound, it's like on this derivative term, it's like then you can get a upper bound on the error which you're making, right, from this error term. Okay, all right. So let me also, well, actually, let me just stop here for now. It's like, and then the next thing I'll talk about is the composite trapezoidal rule.